so that like.
Okay, ma'am.
Yeah, it's written over there, but I mean.
You're able to listen me, ma'am?
Yeah, you are audible, ma'am.
So these are the programs generally we conduct every year on occasion of Science Day, National Science Day, International Science Day. We conduct many competitions for the students, inter as well as intra-collegiate competitions, and where our students participate. 2 days like that, we conduct the symposium and conferences. And by inviting these are the toppers, ma'am, who have come from last year, from semester exams, and we take and we are giving gold medals for the students who are topped in their exams. And this is the last year we conducted webinar by Satyanarayana sir and Karla madam, extension lecture. And this is the alumni meet of our passed out students. And this is the library of our college.
Okay. Very nice.
Alumni meet. And is a national seminar from chemistry department, and we take online class as well as PPT classes for the students. And this is the lab where we will be conducting the practicals. And there's a science exhibits like thing where students will draw and poster presentations like that they conduct. And this is auditorium, ma'am, where 1,000 people gather and we have the programs and other conferences over there.
Really beautiful.
This is a seminar room. And these are classrooms. And this is our labs. Classroom where students are presenting the seminars. And this is also for national webinar. Students were presenting posters. Roja Rani madam, who was the principal of Women's College, she also visited on one national science day.
Oh, good. Very good. Nice presentation. Because I came to know about your college. Really.
Thank you, ma'am.
Yeah, congratulations. It's very good, really.
Still many more programs we have done, but due to shortage of time, we couldn't cover all of them, ma'am.
I know. But still, it is good introduction, I can say.
Thank you, ma'am. Thank you.
అది కూడా నువ్వు చెప్పు ఎగ్జామ్ బ్రాంచ్ చేపిస్తే ఎగ్జామ్ బ్రాంచ్ కూడా ఒకటి కావాలని నాకు తెలిసి సరే ఉన్నారా మేడం
Good morning, one and all. I, Pranita,
good morning.
Organic Chemistry. I'm Pranita, ma'am, lecturer in Organic Chemistry.
Good morning, ma'am. Good morning.
Good morning, ma'am. It's my privilege to welcome you all for today's International webinar on the topic Conformational Analysis. I extend my warm welcome to our today's guest speaker, Dr. Swarupa Rani, ma'am. Of course, madam is not our guest. She's one among us because madam has already sharing her knowledge in the previous day.
Thank you.
I welcome our director of Keshav Educational Society, Dr. J. Nageshwara Garu, and our principal, Dr. Someshwar sir, faculty members and from different colleges and students from our different colleges to this national webinar. I hope you all will definitely acquire knowledge at the end of this session. Thank you, ma'am. Thank you for accepting our invitation.
Thank you.
And now I request Sindhuri, lecturer in Analytical Chemistry, to give an introduction of our guest speaker.
Thank you, ma'am. Good morning, ma'am.
Good morning, ma'am.
I am Sinduri, lecturer of analytical chemistry.
Good.
Dr. A. Swaruparani, Assistant Professor, Department of Chemistry, University College for Women, Koti. Completed BSc from Kakatiya University with the University 5th rank. Completed MSc and PhD from Osmania University. Taught 10 years abroad before joining in Osmania University. Taught 5 years in Center of Higher Secondary Education, Mail, Maldives, London Edexcel syllabus, and received many awards for excellent results and most popular teacher among the students. Taught 5 years in Eritrea, Northeast Africa in higher secondary school and the Eritrean Institute of Technology. Joined in Osmania University in 2013 September and working till date in University College for Women, Koti, teaching to BSc and MSc students. Thank you, ma'am.
Thank you.
Video on 11.
Now I request Madam, you can start the session, ma'am.
Yeah. Thank you for the nice introduction, Sinduri ma'am. Thank you so much. Please give me a few minutes to start, okay?
Okay.
Ma'am, is the screen visible?
No, ma'am.
No. Okay, ma'am. Just give me 1 minute. How about now, ma'am?
No, ma'am. Not visible.
No. Okay.
One arrow mark will be there, ma'am, in between. After hand symbol, arrow mark will be there. That I have to press, ma'am. That is the present screen.
Yeah, that's what I have done. Just I'm checking, ma'am. Just give me some time. Now also I think it's not visible, no ma'am?
No, ma'am.
Okay. How about now, ma'am?
Okay.
Not visible? Is it visible, ma'am?
No, ma'am.
No. Okay, just maybe I need some help. Just okay, just ma'am. Because last time I have tried and I got on my own. But yeah. I'll call someone, just ma'am.
Okay.
By chance, is it visible now? No.
No, ma'am.
Okay, ma'am. Just give me 1 minute. Srinivas? Srinivas? అయ్యో నేను షేరింగ్ గూగుల్ మీట్ లో నాకు షేరింగ్ ఇది రావట్లేదు ఫైల్ ఏం చేయాలా
దేంట్లో మేడం గూగుల్ మీట్
లో
మీట్ లో అడ్మిన్ కి ఉంటుంది మేడం షేరింగ్
అంటే ప్రెజెంటర్ కూడా ఉంటుంది బట్ ఐఎమ్ నాట్ గెటింగ్
గూగుల్ మీట్ వాళ్ళకి కనిపించట్లేదంట
స్క్రీన్ షేరింగ్ కనిపించట్లేదంట అది ప్రాబ్లం
ఒక్క 2 minutes టైం ఏంటి మ్యామ్ నేను గూగుల్ చేసి చెప్పేస్తాను
ఒక తొందరగా Ma'am, am I audible?
Yes, ma'am. Yes.
Ma'am, sorry for the inconvenience. Somehow I don't know because the same application, but
Yes, ma'am.
I could not share. Why I'm not getting that? To share the current screen, you need Google. Okay.
Madam,
Ma'am, yeah, still I'm taking time. Ma'am. I opened them, those documents. I can see them, but I don't know. I could not share them. So I'm just checking and I asked someone also to check it.
no, madam, did you find the share option, ma'am? One box
Yeah.
is there with upward arrow mark.
Yeah, that is presentation, right?
Yes, that is
yeah.
presentation.
So it says share an application window. Chrome wants to share the contents of your screen with the meetgoogle.com. So for that, the contents, actually I opened them, but I cannot, I don't know what's happening when I want to share them.
Okay.
Because last time I can see them when I share the application,
Yes,
but now they are not visible here. Maybe I'm missing something because now I'm doing from college. So just I asked some people. So they'll be just give me a few minutes. Sorry for the inconvenience.
Okay, no problem.
Yeah. Image seamless? చూసిరా అదే నా మొబైల్ చూడండి అది గూగుల్ కి షేర్ అవ్వట్లేదు డాక్యుమెంట్ గూగుల్లో షేర్ చేయాలి డెస్క్టాప్ మీద ఉంది అదే అవ్వట్లేదు కదా వీడియో నాట్ ఆఫ్ ఎలా here share an application ఇది ఇందులో ఉన్నాయన్నమాట అబౌట్ అవి రెండు దే ఆర్ ఓపెన్ యాక్చువల్లీ బట్ ఐ కుడ్ నాట్ షేర్ దెమ్ actually cancel and మళ్ళీ గోనా now ఇందులో లేదు, ఇగో ఇక్కడ ఉంది ఇందులో.
మీరు ఒక పని చేయండి, ఫస్ట్ మీరు ఓపెన్ చేసి డెస్క్టాప్ మీద పెట్టండి.
అది ఓపెన్ చేసి ఉండే డెస్క్టాప్ మీద, రెండు డెస్క్టాప్ మీద. ఇప్పుడు వచ్చేసింది.
ఇదా?
ఇదే కరెక్టే. అదే పోయినసారి ఈజీ షేర్ చేసిన, ఈసారి అందుకు అవ్వలేదు.
చూడండి.
థ్యాంక్ యూ. ఐ థింక్ వచ్చింది. థ్యాంక్ యూ. Good morning and sorry for the inconvenience. I think it will be okay now, right?
Yes, ma'am. Now it's visible.
Actually, we have a power cut, and as well as I don't know, because last time it was very easy for me, but now when I clicked, there was something. Okay, and sorry, because I never do okay. So, students and all the faculty and everyone who is present in the webinar, thank you so much. Thank you for giving me the opportunity. And let me start the conformational analysis. Students, I hope you will get at least something, because your teachers are very good and they are explaining you everything, it seems. But if you get few points extra, that will be something for you. So let's start the conformational analysis of the acyclic systems. We have in this SEM only about the acyclic systems, not about the cyclic systems. Okay. So what is meant by the conformational analysis? How do you define? See, when we start any topic, we should be able to say what that topic is going to discuss about. So this conformational analysis is going to discuss about what exactly? It is going to discuss about the energetics of the different conformations, what we are going to do. That means the relative stabilities of the we will be doing. Then you can say, why do we need the conformations, and why do we need the energetics of the conformations and all those? Because these conformations are very important when we want to know about the rate of reactions and the reactivity of the molecules. For that reason, we'll be going for the conformational analysis. So conformational analysis will be dealing with the energetics of the conformations, relative to the rate of reactions. Okay. Then next one, where are they helpful? Because when you are studying something in our life, it should be helpful somewhere, right? So where it is going to help us? First thing, as I mentioned, it is going to help us in finding what's the relationship between the conformation and the reactivity. And the second one, it is going to help us when we want to get the structures, especially when we are doing the research on the structures. Then if we want to know what is the structure of the drug we are designing, for that it will be really helpful to us. Then it will also help us to understand the stability of the different isomers, because depending on the stability, there will be transition states, activation energy, etc. So how the stability is going to affect our chemical reactivity of the molecules and the reactions at the rates, everything we will be getting from this. And also we'll be predicting about the product selectivity. That means what is the stereochemistry of the product, what we are going to get, and how the mechanism is occurring in that reaction, and what are the rates of reactions. That means is every molecule, is every conformer of the molecule acting or the reacting with the same activity, or the reactivity, or the rate of reaction differing. All those we are going to do this topic. Then, this topic is related to the stereochemistry. You know already what is stereochemistry. It is the study of the relative spatial arrangement of the atoms within the molecules, and it will be studying about the static as well as dynamic effects of the three-dimensional molecule. molecules. Okay, so this time I thought of slide sharing, but again, because of all the structures and all, I went for again the same thing, CAM scanner. Then in this topic, we will be doing about the conformational. Okay, as I mentioned, the conformational analysis topic is going to deal with the energetics of the conformations, relative stabilities, and what is the effect of the conformation on the reactivity and rates of the reactions. Then in this, when we say conformations, what is meant by the conformational isomerism? Because before we start, if we know certain terms, that will be very clear to us. So this conformational isomerism is also a type of the stereoisomerism, because you have done enantiomerism, diastereomerism, because enantiomers and diastereomers, they are the part of your topics. So these are conformational isomers, also stereoisomers. But remember, these stereoisomers are the conformational isomers can be interconverted by rotation about the single bonds. You know, when you start analyzing about the rotation around the bonds, single bond will allow the free rotation. Whereas if there is a double bond, then the pi bond will be restricting the free rotation. So these conformations are the synonyms, what you can call conformational isomers, conformers, rotamers, all these will be representing the same term. Okay. So the conformational isomers are the stereoisomers and interconverted by rotation about the single bonds. Let's say there are two structures which cannot be interconverted by rotation about the single bond. Then you cannot call them conformations. They might be stereoisomers like diastereomers or maybe enantiomers. You call them conformational isomers, you should be able to convert one conformer into the another by rotating the single bonds. Usually carbon-carbon single bonds. For example, see, don't go into the details of the energies and all those things. Just I took it as an example. So if you take N-butane molecule with the 4 carbon atoms, where if you take, normally we will be representing these structures are the conformers in the Newman projection formula. You have done in the stereochemistry how to draw Newman projection formula, how to draw Sawhorse, and how to draw three-dimensional wedged formula, flying wedge, and all those, and how to interconvert them also. So here we are taking the second carbon as the front carbon. So here the dot, okay, in the center, whether you show it or not, that is the front carbon, which is bonded. This is the second carbon in the N-butane structure, which is bonded to one methyl group, 2 hydrogens here, and the another bond is with the third carbon. That third carbon is represented here as a circle, which we call it as a back carbon or the rear carbon. Again, the third carbon is bonded to one methyl group and 2 hydrogens. So that is what the representation of the Newman projection. We take front carbon here, in this case for N-butane, that is the second carbon, rear carbon, that is exactly back of this, that is the third carbon. Then we represent the groups bonded to it. So front carbon just by dot, and the 3 groups are the atoms that are bonded to it in this 120 degrees angles we will show, and the rear carbon will go exactly back of this, and that will be represented by the circle, and the other 3 groups bonded to it will be represented like this. So in this, the arrangement can be, see here, the difference. What are they and all? We can take it later. See here, 2 methyl groups are side by side. That means the front carbon and the back carbon methyl are separated by, if you take the angle, that is 60 degrees. What is that angle called and all? We will take later. So here the 60 degrees, which of course known as Gauche, what is Gauche, anti, and all those again we will be taking. Now I don't have to explain them. So just consider first to second, second to third, and third to fourth structure. All of them are representing the same molecule in butane, but the difference is in the arrangement of the groups. Here 2-methyl and here 2-methyl, 180 degrees, here 60 degrees, here 60 degrees, but other side, and here 0 degrees, like this. So these different arrangements of the molecules, which can be interconverted by rotation about the single bonds, are known as conformers. Of course you know them, but when I'm explaining I have to make it what is what. So for that reason, then our syllabus says that introduction to dynamic stereochemistry. What is meant by dynamic stereochemistry? Dynamic is which is not static, which is in the movement. Okay, so this dynamic stereochemistry will study what is the effect of the stereochemistry on the rate of chemical reactions. Because in most of the reactions you have in the unit 1 stereochemistry, you will be doing some reactions. In the reaction mechanisms, you will be doing some reactions with the mechanisms where stereochemistry will play a lot of role in the course of reaction, how is it taking place, and also in the product stereochemistry, what are they producing. So all these will come under dynamic stereochemistry. So here, all these examples you will be doing either in the stereochemistry topic or reaction mechanisms, or in the conformational analysis. In one or the other units, you will be doing all these reactions. All these reactions, stereo-specific reactions, means here the stereochemistry of the product will be depending on the stereochemistry of the reactant. If you remember the addition of bromine to alkenes, when you take cis-2-butene, it will be producing one product, and trans-2-butene will be producing some other product. Cis-2-butene will be giving you the racemic mixture, trans will be giving you the meso. So that will come under stereo-specific reactions, because the product stereochemistry will depend on the stereochemistry of the reactants. If we say stereo-selective, then in that case, the product stereochemistry doesn't depend on the stereochemistry of the reactants. Whether you take cis or trans, it will be going to produce the same product. Then regio-selective means one of the regio-isomer, that means the constitutional isomer is produced in large quantity when compared to the other. Then enantioselective means in that 2 enantiomers will be produced, but one of the enantiomer is produced in the large quantity when compared to the other enantiomer. Then diastereoselective means in that 2 diastereomers will be produced, but 1 diastereomer is produced in large quantity when compared to the other. A symmetric synthesis. In this, what we do is we start with the achiral reactant, but finally the product what we get will be chiral, that means optically active product. That means optically inactive is going to produce optically active one. Then the racemization process. It is the reaction in which the racemization takes place. That means you will be getting the 2 enantiomers as the products. Sometimes they may be equal to get the racemic mixture. Sometimes even the one of the enantiomers may be more or less. Depending on that, we get the percentage of racemization. So all this will come under dynamic stereochemistry. So you will be doing all this in one or the other units. Then maybe if not this, simply we might be doing about the conformational transformation, that means the interconversion of the conformers we will be doing. Or maybe in this we will be correlating simply the stereochemistry of the starting materials and the products in terms of the transition states, or maybe the intermediates, or maybe in terms of the activation energies, so that we will relate what is the reactivity depending on the conformation. So those things we will be doing in this. Then you know very well about the diastereomers. They will be differing significantly in their chemical reactions with respect to the rate of reactions. Whereas enantiomers, they will be having the same rate of reaction, but the diastereomers will differ in the rate of reaction. Then when you do the conformational theory, mainly we focus on the relationship between the reactivity and the conformation. Okay, so here the principle of this topic, conformational analysis, is to study the effects of the conformation on the chemical reactivity. So this is what the introduction, because your syllabus says very clearly about the introduction to dynamic stereochemistry. Of course, isomers I don't have to, because you know them already. They can be constitutional isomers or stereoisomers. Under constitutional, all the general isomerism, what you do, chain, position, fractional, tautomers, metamers, valence isomers, all those will come. So now we go for the stereoisomers. Of course, you have done them already in the stereochemistry and other topics as well, in the degree as well. So here, what happens in the stereoisomers, they will be having everything the same functional group, same molecular formula, everything, the connectivity of the bonds, everything will be the same. But they only differ in the spatial arrangement of the atoms, that means the bonds in space. Now, we are concerned with this. Then stereoisomers can be two types. Conformational isomers, that is our topic. Conformational isomers and configurational isomers. Conformational isomers, here, they differ only in the conformation. What is meant by the conformation, you know, that is about the structure or arrangement of the atoms in a molecule. And you know, these structures or the arrangement of atoms in the conformers can be interconverted by rotation about the single bonds at room temperature. You don't have to go for heating and all. Or maybe in presence of the light and all, we don't have to. At the room temperature itself, these conformers will be converted from one conformer to the another. And other, I told you, they have the same connectivity because they are the stereoisomers. And here, what happens, they will give temporarily different shapes of the same molecule. Different shapes in the sense the groups which we show will be different in their angles, dihedral angle. What is that? We will see it later. Then these conformers, of course, they are known as rotational isomers. So here, rotation, it will be about the single bond. Here, in the cycloalkanes, you know, if you are taking cyclohexane, it will be existing in the chair conformation. These two chair conformations are interconvertible by rotation about the single bonds. Therefore, these two are known as conformers. So anyway, study is restricted to only acyclic compounds. So the other examples, what I take will be acyclic. Then here the other one, amine inversion. Here, when you take any amine, okay, that is primary amine. Here we have here, of course, this is secondary amine. Whatever the amine you are taking, nitrogen will be having 3 bonds, and there will be one lone pair. So that lone pair, so when compared to the other structure here, what is happening? These two are the invertomers. So if you rotate this by 180 degrees, you will be getting this. Both are known as invertomers, that is umbrella inversion. Anyway, we don't have to, but if you come across somewhere, you should be familiar. So just for that, under the conformational isomers, we'll be considering them. But we are going to do only acyclic organic compounds. Then what is main in this topic is conformational isomers are classified into conformational enantiomers and conformational diastereomers. So our study is confined to this. Then configurational isomers. The other type of the stereoisomers are the configurational isomers. The difference between conformational and configurational, because you should not think they are the same. Why? Because configurational conformational isomers, they cannot be interconverted by rotation about the single bonds. If you want to interconvert them, definitely you have to break at least one bond. One or more bonds have to be broken in order to convert isomer into another. They are the enantiomers and diastereomers. So configurational enantiomers, they are the configurational diastereomers. For configurational enantiomers, the enantiomers, what all you have taken in the stereochemistry and other topics, they will come with R configuration and S configuration. Both will be non-superimposable mirror images. Here, if you want to convert the molecule with S to R, then definitely you have to break at least one bond. Then only we can interconvert. Then other type of the configurational isomers, of course, they are the diastereomers. Examples, the geometrical isomers, cis-2-butene and trans-2-butene. Unless you break at least one of the bonds, you cannot convert the cis into trans or trans into cis. So this is not our topic, but at the same time, when we are going to use what is meant by that, for that I have used this. So enantiomers and diastereomers will come under configurational isomers. Our conformations will come under conformational isomers. Remember that. Then here, the other point, why the conformational isomers can be interconverted at room temperature, why the configurational isomers cannot be interconverted and we have to break one or more bonds, because here the energy barrier to convert one enantiomer into another or one diastereomer into the another in the configurational isomers will be having the energy greater than the 100 kilojoules per mole. Normally, for the stereoisomers, the energy barrier is greater than 100 kilojoules per mole. That is not available at room temperature. But if you want to convert the conformations, conformational isomers, then the energy barrier is low, that is less than 60 kilojoules per mole, which is available easily at the room temperature. Therefore, one conformation can be easily converted into another. Because why they can be converted, why they cannot be converted, that logic if we understand, then always, understanding will give us the better knowledge to write in the exams or to explain to someone, or even for you, that will be very good, that will help in other topics as well. So the conformational diastereomers, as I have mentioned, here the conformational isomers can be conformational diastereomers and conformational enantiomers. That's what the next line in your syllabus says. So what is meant by conformational diastereomers? Simply first you can say they are the diastereomers. Okay, then why are they conformational diastereomers? Because these diastereomers can be interconverted by rotation about the double bonds. They are the conformational diastereomers. And remember, when you say diastereomers, they are not the mirror images of each other. They are also non-identical. Okay, so here that's about the conformational diastereomers. I'm sorry, here don't consider the name, please. Only take the structure. Okay, the name is wrong here. This is 1,3 butadiene. This is also the same, 1,3 butadiene. But these two structures are interconvertible. Please ignore the names because the names are not related to this. Okay, so here this structure of the 1,3 butadiene and the other structure, they both are not the same. That's not the same conformations, because when you consider the single bond between the second carbon and third carbon, here the two double bonds are on the same side, like cis you can say, and here the two double bonds for the second carbon and third carbon are across. That means trans you can say, but it's not 2-butene, it is the buta-1,3-diene. So these two structures, you can consider them as the conformational diastereomers by rotation about the single bond. If you rotate this, then automatically you can get this structure here. If you rotate this carbon by 120 degrees, then you will be getting this. Okay, so So like this, by rotation, you will get them. Maybe it is not the appropriate example because mostly you will be doing the Newman projection. So take the ethane molecule, which is the staggered conformation, and the other one, which is eclipsed. So if you rotate, the rear carbon by 60 degrees. So the rear carbon is the back carbon by 60 degrees. Then what happens? This hydrogen will come here. This hydrogen will go back of this, and this hydrogen will go back of this hydrogen. So here, this is the eclipsed conformation. Of course, staggered eclipsed, how to say that we will take up later. But these two structures can be easily interconverted by rotation by 60 degrees. Either you can go for the front carbon rotation or the back carbon, because here both carbons are having identical groups. So staggered ethane and eclipsed ethane should be considered as conformational diastereomers. Butane, NButane, this is anti-conformation where methyl groups are at 180, and here the methyl groups are at 60. This is the Gaussian conformation. Again, these two, neither they are the mirror images or they are identical. So they are supposed to be conformational diastereomers. Like this, you will find in the textbooks many examples. Here, you get the tartaric acid. These are again all conformational diastereomers because they are not identical and they are not mirror images. So, the conformational diastereomers. Again, this is another example where this is 1,2 diphenyl ethane, 1,2 diol. Anyway, names are not required, but check these two structures. They are not the same. They are not the mirror images. So conformational diastereomers. Again, these two with the different groups, conformational diastereomers. Okay. Then what is meant by conformational enantiomers? You know what is meant by enantiomers? They are the non-superimposable mirror images, right? They are the stereoisomers. So conformational enantiomers are the conformation of the isomers that are non-superimposable mirror images of each other. So here, this is the Gaussian conformation because 2-methyl at 60. This is also Gaussian with the 2-methyl groups at 60. But these two can be interconverted if you rotate them by 120 degrees. So here, this rear carbon, if you rotate from here to here 60, from here to here again 60. By 120 degrees, you will be getting the Gaussian. Now check these two. These two are the non-superimposable mirror images. So they are the conformational enantiomers. So for this is N-butane molecule. Like this, you can take other like meso 2,3-dichlorobutane. So here, instead of hydrogens, what we have taken in N-butane, here the second carbon and third carbon will be having each carbon one chlorine atom. So these two structures, again, you can consider them as non-superimposable mirror images. Therefore, they are the conformational enantiomers. Like this, you can take different examples from any textbook. You will find a lot of examples. Here, 2R, 3R, tartaric acid, 2S, 3S, tartaric acid, these two again, they are the non-superimposable mirror images. Like this, you can go for any. So I have covered what is conformational analysis, what's introduction to dynamic stereochemistry, and according to the syllabus, you have conformational diastereomers and conformational enantiomers. So I covered them. Now, before we do the conformational analysis of the examples, what we have in the syllabus, because mostly if you go through the past papers, of course, it doesn't mean you should get the same question from the past papers, but at the same time, mostly this syllabus of conformational analysis is dominated by conformations, and which are the preferred conformations, and which are more stable conformations. To understand which one is more stable, which one is less stable, why one conformation of the same molecule is preferable and one conformation of the other molecule is not preferred one, are highly unstable. To understand those things, certain terms we should understand. For that, the first one, what we have to know is the dihedral angle. Okay, so what is meant by dihedral angle? Because normally when we take gauche, then eclipsed, we will be showing the Greek letter that is theta, which represents the dihedral angle. So that we will be using. But what exactly meant by that? See, many students do know, but there will be always few students, always they get confused. What is this dihedral angle? So dihedral angle is the angle generated by two intersecting planes. Let's say our molecule has carbon-carbon bond. This is having hydrogen. This is also having hydrogen. So this is like open book, I can say. So this CH is on one plane, this CH is on the other plane. So if you are taking the angle here, then that angle, what is that angle you are considering? You are considering the angle between hydrogen. If you say this is C1, this will be C2. Okay. Or you can consider the angle between hydrogen, and if you take this as C1, this will become C2. So like this, the angle between the hydrogen, carbon, carbon, or you can say the hydrogen, carbon, carbon, whatever you consider. When you show the Newman projection, instead of hydrogens, I have shown them as X and Y. You can take them in place of hydrogens. Then the front carbon is having X and the back carbon is having Y. So, what is the angle between the two planes when you consider XC, that is the front carbon, the C2, that is the back carbon? Or you may take what is the angle between the Y, that is on the rear carbon. Then next you can say C2, that is the rear carbon. Then C1 is the front carbon. So whatever, that's the angle between X, C1, C2 or Y, C2, C1. So that will be considered as the dihedral angle. Normally when we explain the different conformations, we will be using the dihedral angle. And the another term what we'll be using is the torsion angle. Okay, torsion angle is the angle between here, the carbon-carbon planes, how these two hydrogens are making the angle on these two carbon atoms. That will be important when we do the Klein-Prilog nomenclature. So there you will be considering HCCH. So how these two hydrogens are making the angle on the carbon atoms will be considered as the torsional angle. That is also important, but here we will be using only dihedral angle. When we are discussing the different conformations, sometimes we also use the torsion angle. Torsion angle will consider all the four atoms, and that is the angle between the two hydrogens which are making on the carbon-carbon bond. Now, when you take the Newman projection, you know usually how do you represent the dihedral angle theta. See, this is the eclipsed conformation. You know what is meant by eclipse. I don't have to give you, but at the same time, eclipsed is very high energy conformation, especially for alkanes like ethane, butane, propane. If you are taking the eclipsed conformation is the highest energy conformation. And remember, in the eclipsed conformation, what happens? The front carbon and the rear carbon hydrogens. This is the ethane molecule I am taking. The front carbon hydrogen and the rear carbon hydrogen are eclipsed. Eclipsed means one hydro, that is the rear carbon hydrogen is exactly behind the front carbon hydrogen. That means the angle here, that is the dihedral angle. I told you that dihedral angle is the angle between the two planes will be 0. So between these two hydrogens, there will be 0 dihedral angle. If the dihedral angle between the two groups are atoms on the front carbon and rear carbon 0, then that will be the eclipsed conformer, and eclipsed conformer is usually high energy conformation in case of alkanes. Now, consider between these two hydrogens, the angle is 60 degrees. That is, if you consider these two hydrogen conformations. That staggered conformation arguments and staggered conformations will be the low energy conformations. You know, of high energy conformation means saying here, because here what is happening is in the low energy conformation of the staggered, here the angle will be either 60 or 120 or 180. That means there is maximum separation between the groups. So always the staggered will be more stable than eclipsed, because eclipsed at higher energy, less stable. Staggered at low energy, more stable. Then what are the types of strains we have to know in order to explain the stability of the molecules? So here the types of the strains, what we consider are the steric strain, torsional strain, and angle strain. So if you say steric strain, of course, I'll show you with the structures also. But before that, the steric strain here, okay. So here, this is the meaning of the conformations, what I have shown, maybe with the double bonds or maybe just with the single bonds, these two. This is the low energy conformation. Here, the lower energy conformation. Okay, because the two methyl groups are far apart, 180 degrees. Here, two methyl groups are at 60 degrees. So when compared to this, and this is having higher energy, therefore more, the less stable conformation according to the Newman projection formulae of the N-butane, what I was showing. Then what is meant by conformer and all I gave you. So I want to show different strains now. First one is the torsional strain, because the stability of these conformers will be depending on what I have mentioned, three kinds of the strains. First one, okay, you can go in any order, torsional first or van der Waals first, it doesn't matter. So one is the torsional strain. Torsional strain is also known as eclipsed strain and also Pitzer strain. All the three will refer to the same strain, which is the torsional strain. This torsional strain is because of what? It's because of the repulsion between the electron pairs in the bonds. Okay. And remember, the torsional strain arises when there is repulsion between the electron pairs in the bonds which are not attached to the common atom. For example, take the front carbon. On the front carbon, this hydrogen and this hydrogen, all the three hydrogens are bonded to it. So if you consider the repulsion between this hydrogen carbon bond pair and the same carbon hydrogen bond pair, then that will not be considered as a torsional strain. For the torsional strain, it is the strain caused by the repulsion between the electron pairs in the bonds that are not bonded to the same carbon atom, are not bonded to the same atom. That means this is resistance for the bond twisting or bond rotation. You get this when you rotate one conformation into another, then definitely there will be dihedral angle will be changing. That means the torsion angle also will be changing when you rotate one conformer into another, or when one conformer is converted into another, there should be rotation about the single bond. So that rotation causes the repulsion between the electrons in the bonds which are not bonded to the same atom. So I'll consider here in the eclipsed, this front carbon CH bond pair will be repelling the CH bond pair on the rear carbon. So what happens in the eclipsed formation? There is torsional strain present in the eclipsed conformation. Why the torsional strain has arisen? Because when the staggered conformation is converted into the eclipse by rotation about the 60 degrees dihedral angle or torsion angle, then here there will be repulsion between the electron pairs in the bonds on the adjacent atoms, not on the same atom. So this torsional strain will cause that conformation to be at higher potential energy. See here, in the staggered conformation, we don't have the torsional strain because the hydrogens are as far apart as possible. So when compared to the eclipse, here the repulsion between the CH bond electron pairs on the front carbon and the rear carbon will be minimum. So we don't expect the torsional strain in staggered. But when it is converted into eclipse, what's happening? The rear carbon hydrogen and the front carbon hydrogen dihedral angle is becoming zero. So they are coming very near. So one bond electron pair will be repelling the other bond electron pair on the rear carbon. That is the reason for the torsional strain. Torsional strain is caused by the repulsion between the electrons in the bonds. So what happens because of the torsional strain? Because of the torsional strain, that conformation will go to higher potential energy. Less torsional strain means it will be at less potential energy. So always the conformation at higher potential energy is less stable when compared to the conformational at lower potential energy. That's why when you are explaining the conformations, make use of the torsional strain and compare it in different conformations. Then the second strain in the molecules here in the conformations is the van der Waals strain. That van der Waals strain will arise when here also again there will be repulsion between the electron pairs in the bonds, but this will arise due to the size of the atoms when you force, on the front carbon, rear carbon groups which are bulky or which are in larger size, closer to one another or into the common space, then this repulsion will arise. And in general, what you can say is van der Waals strain will arise, if the position of the two groups or the atoms are closer than the sum of their van der Waals radii. Van der Waals radii is half of the distance between the two molecules, that is the internuclear distance between the two nuclei when they are not bonded to each other. For example, take two hydrogen atoms. You can keep two hydrogen atoms at some proper distance only. If you bring them much closer than that, then what happens? There will be repulsion. So what is that minimum distance? And you take the internuclear distance between the two hydrogens and take half of it, that will become the van der Waals radii. So there should be minimum distance between the two atoms. So there should be minimum van der Waals radii between two groups. So if that distance is less than the van der Waals radii, then what happens? There will be repulsion between the electron pairs in the bonds on the adjacent atoms, or maybe from far away atoms or groups, whatever. Then here, the bulky size or larger size of the groups will cause this repulsion when you force them closer to one another. This van der Waals strain, in other terms, it is known as steric strain. So that is very important when you explain the different conformations. Here, this is anti-conformation where two methyl groups are far away. So you don't expect the van der Waals strain or the steric strain. But here in the eclipsed, this is also eclipse, this is a total eclipse, this is eclipse. So here what is happening? Hydrogen and methyl, they are very close. So there will be some van der Waals strain or steric strain. But in total eclipse, two methyl groups which are bulky are very close because the dihedral angle is only 0. So that will cause much of the repulsion, and that is known as the steric hindrance here two bulky methyl groups with the dihedral angle 0 will cause the steric strain or van der Waals strain in the molecule. So because of that, this conformation of the total eclipsed one is at very high energy. That means it is highly unstable when compared to just eclipsed, that is between hydrogen and methyl. Is bulky, but hydrogen is a tiny atom. So when you compare the steric hindrance or the steric strain in the total eclipsed and eclipsed will have less steric strain or van der Waals strain. That's why it is at lower energy when compared to total eclipsed strain. Then consider the gauche. In gauche, not like anti, two methyl groups are at 180 or as far apart as possible. But when compared to eclipsed and totally eclipsed, two methyl groups are far and methyl and hydrogen are also far. Therefore, the gauche conformation is the here, which is having little bit higher energy than anti, but at the same time, this is a lower energy conformation than the eclipsed and totally eclipsed. That means in Gauche conformation, there will be less van der Waals strain or steric strain when compared to eclipsed and totally eclipsed, but little bit higher van der Waals strain when compared to anti. That's why this is at little bit higher energy. So use this in your explanation. Then the conformational analysis will be helping us to know which conformation is dominating in our sample, that is given by the mole fraction. If you take N-butane, see here, the mole fraction of N-butane with the anti-conformation is highest when compared to the Gauche. When compared to the other one, what is that? Eclipsed one. But see here, you can't see any eclipsed conformation in the mole fraction. That means only the stable conformations will be existing in the sample what we are taking. So for N-butane, only anti and Gauche are the stable conformations. Anti, most stable, but when compared to anti, Gauche is less stable than anti, but both are stable conformations. That's why they exist in the sample what you are taking, N-butane. So these points you consider whenever you are explaining any conformational analysis. The third one, angle strain, is less important in our topic because we are doing the acyclic systems. But if you go for the cyclic systems, you know there the normal bond angle of the tetrahedral carbon around the tetrahedral carbon is 109 degrees 28 minutes or 109.5 degrees. But if you take cyclopropane and all, here the bond angle will be differing from the normal tetrahedral angle by different degrees. Therefore, there will be some strain in the molecule, that is the angle strain, that is important for the cyclic structures, which we are not doing in this topic. But one point you can see here, 3 to 6, here you can see the angle strain is decreasing because the deviation from the normal tetrahedral bond angle and the bond angle in these compounds is decreasing. The difference is decreasing. That's the reason here the angle strain will also decrease. Later it will increase. Anyway, that is not our point of discussion. But when I discuss this, then I consider the angle strain. Then now, according to our syllabus, we do compounds with what are the conformations, how the stability, all those. According to your syllabus, the first compound is given as ethane. So in ethane, this is around each carbon, you have the tetrahedral shape, two carbons are bonded together. And it is, if you consider the number of conformations for ethane, they are infinite in number. But that's not important to us. What are the preferable conformations? What are the conformations existing in the sample? Or what are the stable conformations? Those are what are the remarkable conformations. Only those conformations we do consider. So if you draw the Newman projection, take one carbon as the front carbon, the other carbon as the rear carbon or the back carbon. Then first place one hydrogen on the front carbon carbon and the second carbon hydrogen exactly back of the front carbon hydrogen, then that dihedral angle will become 0. That's the eclipsed conformation, which is a higher energetic conformation. If you rotate this by 60, then you will be getting on the front carbon hydrogen and rear carbon hydrogen between any two, the dihedral angle is 60 degrees, which is the staggered conformation, where on the adjacent carbons, hydrogens are as far apart as possible. In terms of the energy, staggered is at lower potential energy and eclipsed is at higher potential energy. Now, what all the strains I have explained, you can use them here to explain, because these hydrogens are tiny atoms. That's the reason steric strain or van der Waals strain is not that important. But even if you want to consider the steric strain, which is minimum in this, you can expect it in the eclipsed, not in the staggered, because here two hydrogens are eclipsed. That's a van der Waals steric strain. That is also minimum because of the tiny size of the hydrogen atoms. But the other strain, torsional strain, is here the major factor which plays role. Here, since the dihedral angle or the torsion angle between the two hydrogens is 0, they are very close to each other. That's the reason there is torsional strain in the eclipsed conformation when compared to staggered. Because in staggered, the two CH bond and the adjacent atoms are not that close. But here, they are very close. Here 60 degrees, here 0. Therefore, here in the staggered, there is no torsional strain, but in eclipsed, that will cause the eclipsed conformation to be at higher potential energy, that is less stable when compared to staggered. And at room temperature, easily you can convert. That means these two conformations are easily interconvertible. That is what I can say. So at room temperature, what is the energy required to convert one conformation into another is only 20 kilocalories per mole. But the thermal energy which is available from the surroundings to the ethane is 83.7 kilojoules per mole. Therefore, the ethane molecule can have enough energy to convert one conformer into another. Okay, so here, if you go on taking the conformations by rotating the molecule at the front carbon or rear carbon by 60 degrees, okay, here 60 degrees, then again rotate it by 60 degrees, you get eclipsed, again rotate it by 60 degrees, you get staggered, again rotate it by 60 degrees, you get eclipsed, again you rotate it by 60 degrees, you get staggered. That means here, the energy minima, that is minimum energy conformations are staggered conformations, higher energy conformations are eclipsed. Since all of them are equivalent, you can show only one conformation for staggered, one for eclipsed. Usually when you are taking the dihedral angle, we start with 0, we go to 360 degrees and we represent the conformations. This is the potential energy diagram. It will show how the potential energy of the molecule is changing with the change in the dihedral angle of the conformation of ethane. So for every 60 degrees rotation, you will be converting staggered to eclipsed, eclipsed to staggered. Like that, you will be going on changing. That is for the ethane conformational analysis. If the question is asking you anything, this is all. So only two conformations are important. Okay, one is eclipsed and one is staggered. Staggered will be having lower energy. Eclipsed will have higher energy because of the torsional strain. Then you give here the energy required to convert one conformer into another is very less. That is the 12 kilojoules per mole or 3 kilocalories per mole. That will be easily available at the room temperature. That's all, because these are the things very important. Then before I go for the N-butane conformations, I thought I'll do the Klein-Prelog terminology for the nomenclature of the conformations and the torsional angles. Why is this important? Why should we go for this? As the name is suggesting here, you are going to discuss about the torsion angles. This terminology, Klein-Prelog terminology for the nomenclature of conformations will be based on the torsion angles. I told you the torsion angle meaning is when you are taking A, XY. XY are the carbons. A is the group bonded to X, B is the group bonded to Y. So here is the angle by A and B, that is across the X and Y, is known as torsion angle. So based on this terminology is given. Then you can say why we should go for the extra nomenclature of Klein-Prilog. Already we know which is anti-staggered. Okay, just let me again check once. You might, I mean, it's very clear for you, but at the same time, when do you call anti? When do you call sin? When do you call the other things? Just give me a second, because here the power fluctuations, power cut is there. So just give me a second. Okay, I think I'm back. Okay, so just I wanted to mention, even though it's very clear, just one point I'll be saying, then I'll go back. When do you say anti-conformation? Anti-conformation is if the two substituents on the front carbon and the back carbon, if they are at 180 degrees, then you call them anti. Sin means the front carbon substituent and the back carbon substituents must be having the dihedral angle 0. Here two will be there. Sin, it could be eclipsed with the 0 degrees, or it could be gauche. I mean, okay, sin is only eclipsed with the 0 degrees dihedral angle. Then if it is gauche, there should be always between the substituents on the front carbon and rear carbon. Dihedral angle is either 60 or 300, because we are going clockwise to measure. So here between X and Y, it is 360. That's the reason. See, 300, it looks so much of the angle. So to minimize this angle, Klein-Prilog terminology will be helping us. So anti, sin, eclipsed, gauche, all these, it should be clear. Now we are going to take the different terminology, that is sin periplanar, anti-periplanar, anticlinal, those things. Okay, so before I start, let me tell you why we need Klein-Prilog terminology. Because the sin, anti, eclipsed, gauche, whatever you are taking, they well explain only if the carbon around each carbon, front carbon and back carbon, is tetrahedral in shape. But if one of them is trigonal planar, because if you have one of them is double bond, then it will become trigonal planar. In that case, the terminology eclipsed, gauche, anti, these, they cannot explain well about the conformation. For that reason, we need to go for Klein-Prilog. And always remember, you are taking that the torsion angle, I mean the dihedral angle is always 60 degrees, because we said that between eclipsed and gauche, 60 degrees or 120 degrees. Then between eclipsed and the anti, it is 180 degrees. So always we are going for the multiples of the 60 degrees. But you don't expect always experimentally these angles as multiples of the 60 degrees, because there will be some deviation in the ideal angles. So these torsion angles will consider that deviation. So these are very appropriate. So this Klein-Prilog terminology or nomenclature will be giving us the steric relationship across the single bond in a molecule or a part of the molecule. Remember, you cannot consider the steric relationship between a double bond, because always you show the front carbon and back carbon which are bonded by a single bond. You never go for the double bond. So always it will be explaining the steric relationship across the single bond in a molecule. Then here, torsion angle is also represented by theta. So sometimes the dihedral angle and torsion angle, which one we are representing, we should be we have to always write it, what is that. Then sometimes in some textbooks, they also show us with omega. Then always remember, when I'm showing the dihedral angle, I said it could be 300. But when you are showing the torsion angle, you never say 300. Always you take the smallest value. That means you say 60 degrees even for 300 by inserting plus or minus depending on clockwise and anti-clockwise before the torsion angle that we will see in the example. Then what is the torsion angle? I gave you the torsion angle will be measured in clockwise direction 0 degrees to 360 degrees. And one difference between the torsion angle and dihedral angle is dihedral angle doesn't have the direction, but torsion angle has the direction. Okay, so we are going clockwise, anti-clockwise, whatever the direction is there for the torsion angle. Then how do we know? Because when the different groups are bonded to the front carbon and back carbon, between which two groups we have to take the torsion angle. So for that, the one advantage of Klein-Prelog terminology of the nomenclature is first you have to identify which groups you are considering them as the reference groups, or the technical term is fiducial groups. Okay, how to select them? I'll tell you. First one, if you are having all the different substituents on each carbon atom, then you can go for the sequence rules. When you are giving RS configurations, there you will be using the selection rules. Okay, so there Ingold Prelog rules you will be using. The same here. You're using the sequence rules, identify if there are 3 different substituents, which one should be given the highest preference, consider that on each carbon as a reference group. Let's say if there are 2 identical groups on the each carbon atom, let's say 2 methyl groups or 2 bromine atoms or 2 chlorine atoms, like that, on each carbon atom you are having 2 identical groups. In that case, you go for the non-identical group, that is the third one, as the reference group. Then, in some cases, what happens if all the substituents are the same? That means they are the identical ones. Then, in that case, the one which is giving the smallest torsion angle, you should choose. Okay, that when we do the examples, we will come to know. Then here, normally what do we do is the reference group. What we do is we keep it on the front carbon at the top in the Newman projection. That means this is a Newman projection. So my reference group is A on the front carbon. So I'll keep it at the top. Okay. So for that, it is easy in that way when we write the Newman projection to identify different conformations. For that reason, keep it at the top in the Newman projection formula. Then you can explain them in terms of the different terms what we are going to use for these conformations. Check here. If the angle between the 2 reference groups is, that is a torsion angle, what we are considering between the 2 reference groups is 0 to 90, either plus or minus, then it will be considered as sin. Okay, sin means eclipsed, you can say. Then if the angle between the 2 reference groups is between 90 and 180, maybe plus or minus whatever, you will consider that as anti. Anti means as far apart as possible or staggered. With that, I'll show you how to give it. Okay, first plus or minus 0 to 90 will be considered as sin. Then plus or minus 90 to 180 as anti. Okay, then it could be clockwise or anti-clockwise. Depending on that, we give the plus minus symbols. Then what is meant by periplanar? Because we are going to use that term. Periplanar meaning they are approximately planar. They are not 100% planar, but approximately planar. Clinal, meaning they are inclined or eclipsed, you can say. And here, the torsion angles usually deviate from plus or minus 30 degrees. So, like dihedral angle, you don't have to say just 60, 120 like that. So, these angles may differ plus or minus by 30 degrees. So, the sign of the torsion angle whether you consider the groups on the front carbon and rear carbon. So you may go from front to rear or rear to front. The sign or the symbol, what you get for the torsion angle will be the same, okay, because it will not change. For example, I'm taking on the front carbon A, on the rear carbon B. Okay, then here this is plus 60 degrees. Okay, it could be plus or minus 30 degrees, but normally plus 60, let's say. Then here you consider from the rear carbon. My rear carbon is having B. So if you are reading from the rear carbon, take from B to A. Again, from B to A, this is the plus 60. Okay, so if you are taking between A and this group, that will become minus 60. Okay, so if you are taking between B and the other group here, that will become minus 60. So if it is clockwise, plus. If it is anti-clockwise, minus. So A to B, clockwise, so plus 60. Then B to A, clockwise, so plus 60. So here, the nomenclature is not going to differ. This is plus synclinal. What is that? I will give you. So this is how you will be giving that nomenclature. Torsion angle, okay, and dihedral angle will be represented by the same, that is the term theta. Then if the torsion angle between the two reference groups is 0 to 30, then it is known as plus or minus 30, because either side, clockwise if you take plus 30, anti-clockwise if you take minus 30, then the designation is plus or minus syn periplanar. Syn means eclipsed. Periplanar is almost in the same plane. Then the symbol for syn periplanar is SP. So plus or minus SP. This is nothing but when you take the butane molecule, that's the eclipsed conformation, where one methyl group will be eclipsing the other. That means exactly at the back of the other. I will show you what is eclipsed and all those for butane. Then the theta as multiple of 60 degrees, if you consider, that is 0. Then if the angle between the two reference groups is plus 60 degrees, as I have shown between A and B, here this is the plus 60 degrees. If it is plus 60 degrees, again the deviation can be plus or minus 30. 0 means what happens? This B will go exactly back of A. Then it will become 0. If it is 0, synclinal or if it is 0, syn periplanar. If it is plus 60, that is deviation everywhere by plus or minus 30 degrees. If it is plus 60, synclinal. And the symbol is plus SC. Take the first letters. Then this will be observed in the gauche. That is P clockwise, anti-clockwise only. Okay. Clockwise P, anti-clockwise M we will show. This is the multiple for the 60 degrees 1. Then if you take 120 degrees between two reference groups, that is again clockwise, that's why plus. Then this is known as plus anticlinal and the symbol is plus AC. Then this is in eclipsed conformation of butane. 120 means it is a multiple of 60 degrees. That means times 2. Then 180 degrees, if you consider plus or minus 30 degrees deviation, then it is plus or minus anti-periplanar, symbol is AP. That is in the anti-conformation of the butane, you will see 180 is 3 times of 60. So it is a multiple by 3. Then minus 120, this is anti-clockwise you are taking. Then it will become minus anticlinal. See, plus anticlinal is plus 120, minus anticlinal is minus 120, plus means clockwise, minus means anti-clockwise. So it is represented by minus AC symbol. Again, this is present in the eclipse conformation. Then 120, if you consider here again minus 120, so 360 minus 120, that will be giving you 240, that is the multiple of 4. Then minus 60 degrees, again if it is plus 60 plus synclinal, minus 60 minus synclinal. Minus SC, again it is in the gauche, that is anti-clockwise. Then this is multiple of 5 because 360 minus 60 is 300. 300 is multiple of 5. Then, so this how to apply. Okay, you can see it in the form of a wheel. Okay, in the form of a circle, you can say. So here is the 0 degrees. Okay, then plus or minus sin periplanar. I gave you plus or minus sin periplanar is 0 degrees plus or minus 30 degrees. Then 100 and that is I gave you 90 degrees. Next okay, here between plus 30 and plus 90, that will be 60 degrees here. Okay, so if you have 60 degrees, that is between plus 30 and plus 90, that conformation is known as plus synclinal. Then here, between these two, it will be 120 degrees clockwise, which is anticlinal. Okay, clinal means inclined. Then here, 180 degrees. Okay, between these two, I mean here, from 0 to here, 180 degrees. So if the reference groups are having the angle 180, then you will go for plus or minus anti-periplanar. Again, if it is anti-clockwise, minus 120, here is our reference group, here is our reference group, then it is minus anticlinal. Then here, again, if the reference groups are differing by like 60 degrees, we will say minus synclinal, anti-clockwise, okay, synclinal. So this is what you have to remember. I have shown you in the form of the circle. You can remember top portion, that means plus 0 to plus or minus 90 degrees, it's a sin. Then 90 to 180, whether it is plus or minus, that is anti. Then again 0 degrees plus or minus 30, sin periplanar. 180 plus or minus 30, anti-periplanar. In between, if it is near to 0, like plus 60, plus synclinal, minus 60, minus synclinal. Then plus 120, then that is anticlinal, plus anticlinal, minus 120, minus anticlinal. So this is just enough for you to remember the designation of the nomenclature by Klein-Prilog nomenclature. So this we will see by the example of N-butane conformations. Then sometimes we also use the common designations. If it is 0, the deviation everywhere is 30 degrees. If the dihedral angle is 0, cissoid or eclipsed we say. If it is 60 degrees, P Gauche, then 120, that is eclipsed, but 120, 180, anti, 240 eclipse, then 300 M Gauche. So like this, we will be using the common designations also using the dihedral angle, and we relate them with the Klein-Prilog nomenclature. To understand this, I'll go to the N-butane example. Before that, what are the advantages here? Because these torsion angles will be giving a range of the angle, not like dihedral angle, the exact value. So that is more realistic, because you never expect practically when you measure the angles, they are the same. So this is more practical approach, you can say. Plus or minus will be representing only the direction of the torsion angle, clockwise and anti-clockwise. This you can apply to any molecule or any part of the molecule where if you are having the carbon-carbon single bond, then X and Y, if you are taking them as carbons, A and B are the substituents, which are the reference groups, then you can use it and explain any molecule, any part of the molecule information. Then it also can be used to describe the partial conformation of the polymer chains and rings, especially when you are taking the polymers which are lengthy and very large molecules. There it's not that easy for us to give the conformation, but using this, it will be easy. Even when you take the ring structures, there, it's not that easy to say which one is eclipsed, which one is staggered, which one is anti. But using this nomenclature, it will be easy for us. Now, we take the few examples. After that, I'll go for N-butane. See here, what is the name of the molecule and all? It's meso 1,2-dichloro 1,2-diphenyl ethane. Then check these three conformations. First, how to give the Klein-Prilog nomenclature. On the front carbon, you are having phenyl group, hydrogen and chlorine. So according to Kohn-Ingold-Prilog rules, chlorine will get the highest preference because of its atomic number, right? So here the chlorine is the reference group on the front carbon. Now go to the rear carbon. Again, chlorine, phenyl and hydrogen. So chlorine will get the highest preference. So on the rear carbon, reference group is chlorine. On the front carbon, reference group is chlorine. Now, check the dihedral angle, that is the torsion angle here. So, between the two chlorines, now we are not measuring. So, I cannot go for plus or minus 30 and all those. I can simply say that the angle between the two chlorines on the front and rear carbons must be 180. So, if it is 180, according to the table here, the 180 is plus or minus AP, that is anti-periplanar. So, without any doubt, I'll keep plus or minus AP, that is the anti-periplanar. Then, by interconversion, that means by rotation about the carbon-carbon single bond, front carbon and rear carbon, you get this conformation. Now, what angle and all, that we can take it later. Now, consider the reference groups. Here, chlorine is the reference group on the back carbon. Chlorine is the reference group on the front carbon. Now, check what is the angle between them. The angle is 60 degrees. But remember, when you are measuring the angle, you go from front carbon to rear carbon or rear carbon to the front carbon. So here, if you go from front carbon chlorine to the rear carbon, you are going anti-clockwise 60 degrees. Therefore, this is minus synclinal or minus SC. Now consider again two chlorine atoms. On the front carbon chlorine, on the back carbon chlorine. So front carbon chlorine to back carbon chlorine is again 60 degrees. But this time you are going from front carbon chlorine to back carbon chlorine clockwise. Therefore, this is plus synclinal. So like this, you can ask me, ma'am, why we are not taking the other conformations? Because they are not important for this particular molecule. That's why they did not give you. Then among these three conformations, easily you can say here, two chlorines are far apart, two phenyl groups are far apart. Therefore, there will be less van der Waals strain as well as the torsional strain as well as the dipole-dipole, the other strains. Therefore, this conformation of the anti-periplanar is most stable when compared to other two. So here, my aim is to give you how to name the conformations. So here, again, if you are taking the molecule the same as above, but this is the active one which you are considering. Now check again the reference groups here, chlorines. That's why I did not underline them. So on the front carbon chlorine, back carbon chlorine, front to back minus 60. Therefore, this is minus synclinal. Then here, front carbon chlorine to the back carbon chlorine, again we are going 60 degrees, that is clockwise. Here anti-chlockwise, but here clockwise. Therefore, here we will be taking it as plus synclinal. Then here, between two chlorines, 180. So plus or minus anti-periplanar. Now, among these three, this is the most stable conformation because two phenyl groups are far apart. Of course, there will be Gaussian-like affinity between two chlorine atoms, but still that will be the dominating factor is the steric factor when compared to dipole-dipole interactions between two Cl-Cl bond, that is carbon-Cl bonds. This we will do in detail when I take the example. Now, since I covered what is most stable one. Then propienaldehyde, that's what I was talking. When there is a double bond, that means on one carbon, if it is trigonal planar, then the that is what I can say, eclipsed conformation, staggered conformation, they don't explain properly. So we need client prilog. So here on the front carbon, double bond O, so oxygen should be taken as the reference group. On the rear carbon, this is a propionylaldehyde. This is the first carbon. Back carbon is the second carbon. Second carbon is bonded to the methyl, that is the third carbon. So it's a propionylaldehyde molecule. So here between the two reference groups, that is front carbon oxygen, back carbon methyl, when compared to hydrogens, it should get the higher priority. So between the front carbon oxygen and back carbon methyl, it's 0 degrees. So it should be plus or minus in periplanar. Then now you consider between the oxygen on the front carbon and hydrogen on the here, the reference group is not hydrogen, reference group and the second carbon is methyl. Here, this is 120. There might be some deviation. I told you plus or minus 30, but if it is 120, then you will take plus anticlinal. Then here, between again oxygen and methyl, that is 120, but now it is going anti-clockwise, 120. Therefore, this is minus anticlinal. Okay, so here, then later when we do the propionylaldehyde, I'll give you which is more stable and why it's not required. So if you can understand only N-butane example, then you will be good with the prilog nomenclature, how to give it. Then this, in normal terms, methyl groups are at 180 degrees Dihedral angle. Of course, consider here torsion angle because we are not measuring it. So the anti-conformer where two methyl groups are at 180 degrees. When you consider in terms of the energy, this is the lowest energy conformation. But in terms of the repulsions and all, if you consider, we go for the Klein-Prilog nomenclature, then we go for the strings. So according to Klein-Prilog nomenclature, between two methyl groups 180, so plus or minus anti-periplanar symbol is AP, plus or minus AP. Then again, here on the first carbon, that is the front carbon, methyl is the reference group. On the back carbon, methyl is the reference group. That's why I'm considering between two methyl groups. So again, here two methyl groups. Here, the front carbon methyl and the rear carbon methyl, you are going clockwise 120 degrees. For this is plus anticlinal. Then again, if you rotate this by 60 degrees, you'll get this is an eclipsed conformation because hydrogen is eclipsed with methyl, hydrogen is eclipsed with methyl, two hydrogens are eclipsed. And if you rotate it by 60 degrees, you get the para-Gaussian conformation. Okay, para-Gaussian means it is the clockwise one. That is M-Gaussian is the anti-clockwise one. So here, if you consider the angle from the front carbon methyl to the back carbon methyl, that is plus 60 degrees, that's clockwise. So P we will show. Then 60 degrees is the synclinal as SC will show. That's if you are rotating this synclinal by 60 degrees, you will be the dihedral angle between two groups is 0. That normally we call it as eclipsed conformation. In this case, there are two eclipsed means you can say eclipsed because two methyl groups are eclipsed together. This is the highest energy conformation. That means highly unstable conformation. Then here, the angle between two methyl groups, when you take, that's 0. So it is plus or minus in periplanar. Then when you take again 60 degrees rotation, here you will be getting the two methyl groups in the Gaussian conformation where the angle between the front carbon and the back carbon is going anti-clockwise 60 degrees minus synclinal SC. Then you rotate again by 60 degrees, it is going from front carbon methyl to the back carbon methyl, that is anti-clockwise 120 degrees, so minus anticlinal minus AC. So this is how you will be giving the nomenclature of the Klein-Prilog terminology. This is one of the important ones in the conformational analysis, and mostly you will also get the questions. If you have any doubt in this, please ask. Students, girls and boys, please ask if you have any doubts in this. Please go ahead, Amma, if you have. Otherwise, I'll continue. Shall I, ma'am? Sangeeta, ma'am, shall I continue?
Yes, ma'am. Continue.
Okay. Yeah, okay, ma'am. Am I clear? Like, am I going fast? Like, is it okay?
No, ma'am. It's okay, ma'am. It's okay.
Okay then. Okay, now we will consider the potential energy diagram for N-butane. Whatever the structures I gave you, for those structures we will be considering. But you can take potential energy diagram either by considering the rotation between the two conformers, or you can take in terms of the dihedral angle. So both I'll be showing for N-butane. Okay, so here you check by rotation about the single bond between front carbon and rear carbon. So I started with the anti-conformation, which is the first conformation, if you remember. By rotating by 60 degrees, you are getting the eclipsed conformation. So I'm going in the same order. So from here to here, you are rotating the conformer by 60 degrees. And here, this is the anti-conformation. This is the eclipsed conformation. But remember, not fully eclipsed. If eclipsed fully, but this is partially eclipsed because hydrogen is eclipsed with methane. Then, as I told you, when you are taking anti-conformation, that is where that all the strains, I'll be explaining about the strains all, but remember here only I'm discussing about the energies. So this will be at the minimum energy. That means the most stable conformation of butane is the anti-conformation. The anti-conformation, when you do it by 60 degrees, that means one of the carbons you are rotating by 60 degrees. That is the front carbon. Then you are getting the eclipsed conformation here, where hydrogen and methyl, hydrogen, methyl, hydrogen, hydrogens are eclipsed. So here, due to the eclipsed strain, or you can say the torsional strain, here the molecule will be at higher potential energy. Therefore, this will be less stable than the anti. Then if you rotate again by 60 degrees, you will get the gauche conformation, if you remember. Okay, I have shown you. In gauche, two methyl groups are at 60 degrees. From front to back, this is clockwise. So this is the P-gauche conformation. This is at lower energy than the partially eclipsed one, but this is at higher energy than the anti. Reason, two methyl groups are here at 180, but here two methyl groups are only at 60 degrees. Therefore, there will be some Gauche-like of interactions. That means repulsions will be there between the two methyl groups that will be making this conformation little bit higher energetic than the anti. That means less stable than anti. Again, when you rotate this gauche by 60 degrees, you will get fully eclipsed. See, the energy level of this conformation, which is fully eclipsed, where two methyl groups are eclipsed with the dihedral angle 0. So this is at highest energy in the potential energy diagram. Highest energy means that is the least stable conformation of the N-butane. Then if you rotate this again by 60 degrees, that is the front carbon you are rotating, again you will get gauche. This is, if I told you, from front to back clockwise, here from front to back anti-clockwise. So anti-clockwise is M gauche, clockwise is P gauche. So again, this is at the same energy as the other gauche. Okay, then when you rotate this by 60 degrees, again, you will be getting the same as the other eclipsed conformation, that is partially eclipsed, where hydrogen is eclipsed with methyl groups. Here, hydrogen eclipsed with methyl and hydrogens. So these two eclipsed at same energy, these two gauche at the same energy. Again, when you rotate the eclipsed by 60 degrees, that means the front carbon, you will be getting the anti-conformation. Anti-conformation is at the lowest energy of the potential energy diagram of N-butane. Therefore, anti-conformation of N-butane is most stable. So I'm giving here in terms of energies. Then the least stable is the fully eclipsed conformation. That's why, see, here I have to use the terms fully eclipsed, partially eclipsed. But if I use Klein-Prilog terminology, easily I can say this is plus or minus syn periplanar. Okay, so that is the advantage here. Okay, so here the terminology what we have used will be very helpful to us. Now consider the energies. If you want to convert the anti-conformation to the partially eclipsed, it needs 16 kilojoules per mole. So from higher energy to lower energy, it is exothermic. It will be giving out the energy. From lower energy to higher energy, it's endothermic. So 16 kilojoules per mole energy must be provided if you want to convert the anti to eclipsed. So this is known as the energy difference between eclipsed and anti. Now, the energy difference between these two, which are gauche and anti, is only 3.8. Very small difference here. If you want to convert anti to gauche, you should give 3.8 kilojoules per mole. Then now you consider anti to fully eclipsed, it is 19 kilojoules per mole. This is the conformational energy of the N-butane molecule, where the energy difference between the highly stable, or the most stable and the least stable, should be considered as a conformational energy. So this is the 19 kilojoules per mole. This is the conformational energy to convert one conformer into the other. Here also again the same, eclipse to gauche. Here, if you want to take eclipse to gauche, you have to take 19 minus 3.8. Okay, 3.8 is the difference between anti and gauche. Then here 16 kilojoules is the difference between the eclipsed and the anti-conformation. So these energies, in some textbooks you will find in kilocalories, some textbooks you will find in kilojoules. In whatever the way you can remember, only is how many values, 1, 2, 3. So easy to remember. And the structures anyway you are supposed to remember. This is in terms of the rotation. Whereas in terms of the dihedral angle, almost the same, but there is slight difference. So here the dihedral angle from eclipsed to gauche, then gauche to eclipsed, eclipsed to anti, anti to eclipsed, then gauche, eclipsed. So here, when you are considering the potential energies, the same, but here you are starting with the eclipsed. That means the dihedral angle between two methyl groups here will be 0. Okay, you can see this is the model. Actually, it is colored, but when I scanned, the color did not come. So here you can see, this is the front carbon. The back one is the rear carbon, which is the dark one. Then this is one methyl group on the front carbon. The other one is the other methyl group on the rear carbon. So these two are eclipsed, one behind another, and where the dihedral angle is 0. So that is the fully eclipsed one, you can say. Then if you rotate it by 60 degrees, that means the dihedral angle between two methyl groups is 60 degrees, then you will get the gauche. Then again, if you rotate it by 60 degrees, you will get the dihedral angle between two methyl groups is 120. That is here the eclipsed one. If you rotate it by 180, you will get here the dihedral angle 180 is the anti-conformation. Then when you rotate it by again 60 degrees, that means 180 plus 60, 240, you get eclipsed again. So this I have shown when I have taken the different conformations of N-butane. So for the potential energy diagram, either you can show the variation of the potential energy using the dihedral angle, as I have shown, you can take the rotation. See here, in the anti-conformation, you can see very clearly, this is the rear carbon methyl, this is the first carbon methyl. So they are as far apart as possible. That's why it is the most stable with the least potential energy. Okay, then next comes gauche. Gauche is next most, after anti, the stable one is gauche. Here again you can see the distance between the two methyl groups. Then when you take eclipsed, either here the methyl and hydrogen are eclipsed, that is partially eclipsed, which is at higher energy. Then fully eclipsed, where two methyl groups are eclipsed on the adjacent carbons, is at highest energy. So this is how, depending on the conformations, the energies, and these energies you can also explain in terms of the torsional strain and the steric strain. See here, this is the structure of the butane molecule, where on the second carbon and third carbon, when two methyl groups are in the eclipsed conformation, see, they are very close to one another. another. Because of their bulky size, they cause the repulsion, which is known as steric hindrance, and because they are forced to have this torsional angle by rotation from anti are staggered to eclipsed, so there will be even the torsional strain. So torsional strain and steric strain both will be present in the eclipsed conformation. That's why this is at the highest energy. This is using the molecular model. So there will be very high repulsion between the electron clouds in the methyl groups in the bond, since they are very close to one another. Then, to keep the eclipsed conformations, remember, we have to spend some energy, because you can say how the eclipsed conformational will exist at higher energy, because you have to provide some energy. To keep methyl group and hydrogen in the eclipsed conformation, we have to give, or we have to spend, the cost is 6.0 kilojoules per mole. If you want to keep two hydrogens in eclipsed, you have to spend 4 kilojoules per mole. If you want to keep again hydrogen and methyl, 6 kilojoules per mole. So the total energy must be spent to keep the N-butane molecule in this partially eclipsed conformation is 16 kilojoules per mole. Of course, when I scanned, the print was very light, so it came light. Then if you take fully eclipsed, then the energy cost is 19 kilojoules, because two methyl groups are bulky. So there will be steric hindrance more when compared to hydrogen and methyl. So here the cost is 11 kilojoules per mole between two hydrogens, 4.0 between two hydrogens, again 4.0. So the total comes 19 kilojoules per mole. That means if you want to go for the eclipsed conformation, if you want to keep the N-butane molecule in the partially eclipsed, then 16 kilojoules per mole energy must be spent on that. And if you want to keep it fully eclipsed, then you have to spend 19 kilojoules per mole of energy. That is because here the different energies, when hydrogen is eclipsed, there is only torsional strain because of the tiny size of the hydrogens. When hydrogen and methyl are eclipsed, there is mostly torsional strain, again because of the tiny size of hydrogen. But when methyl is eclipsed, there will be torsional strain as well as the steric strain because of the bulky size of methyl. Then if the two methyl groups are gauche, then there will not be torsional strain, but only steric strain. That's why the energy cost will be different for the different eclipsed and gauche conformations. This will help us to understand why the eclipsed one is at higher energy and the gauche and anti are at lower energy. Because to keep the groups in that conformation, we have to spend some amount of energy. Then only in terms of repulsions I'm discussing now. You have seen that anti-conformation is the highest, that means at lowest energy and highly stable or most stable conformation. That's because here, reason there is no torsional strain because the angle is 180. There is no eclipsed strain, or you can say no eclipsed and torsional both come the same. Then two methyl groups which are bulky are far apart. Therefore, there is no steric strain as well, which makes the conformation most stable. Then comes eclipsed. Why that eclipsed is least stable? This is a partially eclipsed. Okay, partially eclipsed is little bit more stable than fully eclipsed, but it is less stable than the gauche and anti. So that order also we should know. So here there is torsional strain between here. There is no torsional strain between the bulky methyl, but there is torsional strain between the hydrogen and methyl. And also there is eclipsed strain between hydrogen and methyl. So this will be less stable than the anti or gauche. Then here, when you go for the para-gauche, here, two methyl groups, of course, they don't have much of the steric strain, but at the same time, when compared to anti, here, they are close. Therefore, there will be some steric strain. That means there will be van der Waals strain. Then How about the torsional strain? Torsional strain, here the angle is 60 degrees, so that's not the dominant factor. Only steric strain is the dominant factor. In the fully eclipsed, which is the least stable in the potential energy diagram and the highest energy one in the potential energy diagram, is because here two methyl groups are eclipsed with one another. Therefore, there is maximum of the torsional strain because of angle is 0. And because of the bulky size of methyl, there is high steric strain involved. So both strains will make this conformation least stable conformation. Then M gauche, the same as the other gauche. Then partially eclipsed, the same as the other. Now, when you are taking the sample of the N-butane at room temperature, you will find 66% of the anti-conformation and 34% of the para and M gauche conformations. Here, the reason, here anti and gauche all are stable. But when you take the energy order, anti is more stable than gauche. That's the reason anti-conformation is more in percentage when compared to gauche. So the energy order of the anti is more. That means in terms of the energy in the potential diagram, anti is at least energy than the gauche. Gauche is at less energy than the partially eclipsed, which is at less energy than the fully eclipsed. Okay, so this is how the energy order. So the stability order is reverse of this. Fully eclipsed is less stable than partially eclipsed. Partially eclipsed is less stable than the gauche. Gauche is less stable than anti. So the energy order and stability order will go in opposite directions. So I have taken butane in detail. So what all the points I have discussed for butane, you can apply for the other molecules as well. Okay, so that's about N-butane. I'll take some more examples. I think they are not here. So I'll stop sharing. I'll go to the other document. So next example, I'll be taking 1, 2 dihaloethanes. It's similar to N-butane, only in place of the methyl groups, you will be taking halogen atoms. 1, 2 dihalo refer to adjacent atoms are having halogens. If you are taking 2 dihaloethane, the carbon we're having, and you can also go for the derivative of 1, 2 dihaloethanes, that means butanes, propanes, and all those also you can consider. So first, whatever the molecule is given to you in the exam, attempt to draw its structure. Because many students, what they do, directly they want to try to draw the Newman projection. Then there is possibility you might do mistakes. So first draw it in the normal form. Then go for the Newman projection, because Newman projection will explain clearly the conformations, conformation stabilities, and all those things. So here, just like in N-butane, where 2 methyl groups are eclipsed, here 2 halogens. X can be chlorine, bromine, iodine, water. 2 halogens are eclipsed. This is the first carbon of ethane. The back carbon is the second carbon or the rear carbon. So for the front carbon halogen, the back carbon halogen are eclipsed, then that is fully eclipsed conformation. And you know now you have done already for the fully eclipsed conformation of N-butane, which is highly unstable. According to Klein-Kellogg terminology, this is plus or minus syn periplanar. Then now you go for the anti-conformation, where the front carbon halogen and the back carbon halogen are at 180 degrees. So this is, according to the common nomenclature, we call anti. But according to Klein-Kellogg, we say minus R plus AP, anti-periplanar. So here, the two X groups are at 180. Then Gaussian, two X groups are, if plus 60, plus synclinal, minus 60. I think this must be not hydrogen. This is the X group. So minus 60, then that is minus synclinal. Now let's consider which one is most stable and which one is the least stable. So just by looking at them, you can say very clearly, fully eclipsed is highly unstable. Then which one is more stable? Is it anti or Gaussian? So you can say anti-conformation is more stable than the Gaussian. Okay. So just give me 1 minute to keep the battery because we have power fluctuations in our college. Ma'am, here, Sangeeta ma'am?
Ma'am.
Ma'am, I think here the power problem, because it's been a long time, there is no power. I have connected, but it's not charging. There is only 10%, it says. So as long as it comes, I'll continue, ma'am. Okay?
Okay, ma'am.
Because see, from morning we are not having power. That's why it's very dark in the
raining
room.
Also, no, ma'am.
Yes,
it's raining also.
So
else you conclude with just 1 or 2 slides, ma'am, so that we can have the last things and all. And most of the students, they are asking to post the PDF, ma'am. Will it be possible for you to share it?
Definitely. Yeah, definitely.
Okay.
I'll share it, ma'am.
Okay,
I'll share it.
Okay.
No,
Thank
it's
you.
not a problem for. Okay. So with this example, maybe I'll see at least 1 or 2 examples I'll do and stop, ma'am. Okay.
Yes, ma'am. Yes. Okay, ma'am.
Yeah. Okay. So here, just I want you to consider the conformation and check whatever the strains we have discussed, like Steric Strain, Torsion Strain, and other. And in addition to those strains, here you are having the dipole-dipole repulsion. Remember, the CX bond is the polar bond. Therefore, X with more electronegativity, it will be having partial negative charge, positive charge. Even for the other CX bond, it's the same. So when two partially negative charges in eclipsed conformation, then there will be dipole-dipole repulsions. That is the additional repulsion when there is polar bond in the molecule. So here you will be having steric repulsions because two halogens are usually, when compared to hydrogens, they are the bulky ones. So you can expect the steric repulsions. And because of the eclipsed conformation, you can also expect torsional here, strain, then and also dipole-dipole repulsions. Then in anti-conformation, you can expect, it's not eclipsed, so you don't expect the eclipsed or the Pitzer strain, no steric strain because two halogens are far away. You don't expect the dipole-dipole strains also because the CX, they are far away, where the partial negative charges are as far apart as possible. Then in P Gaussian and Meta Gaussian, there is no Pitzer strain or eclipsed strain because the angle is 60 degrees, whereas there will be Gaussian type of interactions between the two X groups. And also when there are two X groups nearby, there will be some dipole-dipole repulsions will be there. So because of all this, you expect the anti with the less strain will be most stable and fully eclipsed. We usually don't draw also because the molecule doesn't exist in the fully eclipsed form. So that is the least stable. Then comes Gaussian forms. And here I took the general example, but X can be replaced by chlorines, bromines or fluorines any. When you take in place X chlorine atoms, that will 1,2-dichloroethane. As I told you, anti is most stable and fully eclipsed is least stable. Then come in between para and meta Gaussian forms. When you take X-ray diffraction studies, it will show that at room temperature, anti will be existing in 73% and Gaussian will be existing in 27%. And also, in anti, there is no dipole moment because two poles, that means two negative poles, are at 180 degrees. So in each direction, there is no direction for the polarity. It will be getting cancelled out. So the anti is zero polarity, that means zero dipole moment, whereas the Gaussian will have the dipole moment of 3.2 dB units, that is given by the experimental studies. So at room temperature, anti form predominates over Gaussian. Because anti is more stable than Gaussian, then if you want to calculate the dipole moment, you can take mole fraction and the dipole moment of the each conformation, then you add up, then you will get overall dipole moment. Okay. Then just I'll mention, I don't go into the details, but at a lower temperature, that is at the 22 degrees centigrade, you will be having anti is much more than at room temperature, 88% and 12%, and this is a dipole moment. Then in the liquid state, anti and Gaussian will exist in the equal proportions. That's a conformational energy, 12.5 kilojoules mole between anti and Gaussian. And here the reason you can say very clearly, when you take the eclipsing, hydrogen and hydrogen chlorine eclipsing interactions are similar in nature, but there is very little when you consider the steric effect between hydrogen and chlorine. So all this is making here the interactions here. The steric in chlorine anti, you don't expect because they are far apart, because dihedral angle 180, but there is some between chlorine and hydrogen when it is eclipsed here because of Gaussian. Again, there is some steric and torsional. I mean, torsional you don't expect in Gaussian, but steric you will be expecting. So what are the strains I have explained? Use them in your explanation. The same as with the 1,2-dibromobutane, the anti is most stable, fully eclipsed is the least stable. And you take in the liquid state, anti 65%, Gaussian 35%. This is how the proportion and the energy, the energy is the 3.5 kilojoules, that is in favor of the anti-conformation. Whereas in the solid state, you will not have any Gaussian, only anti-conformation, that is confirmed by X-ray studies. In gas phase, and Gaussian, of course, Gaussian will be less, but still it will be there, that is 85% and 15%. So I think it's better if I conclude. If you have any doubts, girls, students, boys and girls, please ask. Because the charging is very low, I don't know, it might get disconnected and there is no power. So please, students, if you have any doubts till this, please ask me. And Sangeeta ma'am, if there is going to be like before they complete their semester, if you can give me one more session, then I'll complete it.
Okay. Okay, madam. Okay, we'll have one more session before they complete. Okay, ma'am. Okay. Thank you very much, ma'am. Okay.
My pleasure. So, please ask them to ask doubts. If
students, do you have any doubts? If anybody has any doubts, you can please ask madam. She can clarify your doubts.
Unfortunately, today no power, and also there was some inconvenience because of sharing the document as well.
Okay, ma'am. So, students, any doubts, ma'am? You can ask. You can unmute yourself and you can ask.
Yeah, please, students, you are welcome.
So I think they are not asking any doubts. Maybe they have understood whole topic. That's the meaning. If they don't ask.
I hope so, ma'am.
Yes, ma'am. Now I request our colleague Anjaneyulu sir to present vote of thanks for today's session.
Good afternoon.
Good afternoon. I take privilege to give vote of thanks for today's national webinar. I wholeheartedly thank Dr. Swaruparani Madam for sharing her knowledge in today's
It's
national
my
webinar.
pleasure.
Madam has clearly explained about conformational analysis and study of conformations and dihedral angle and angle strain, in which factors affecting the conformations and which conformation is the stable conformation of the compounds in ethane and n-butane 1,2 dihydroxyethane molecule. Means this is a very vast conformational analysis topic. It is not enough to complete the 1 or 2 hours.
Yeah.
It will take
That's it.
more time, means that is 4 to 5 hours it will take to explain. Even though Madam has clearly explained in short time all topics in conformational analysis. And once again, thank you, Madam.
It's my pleasure.
I also thank our management of Keshav Memorial Educational Society, Director Dr. J. Nageshwar Rao Garu, Principal Dr. Someshwar Rao Garu, faculty, students who all have cooperated in making the program successful. I also extended my vote of thanks to our technical staff. Once again, thanks to one and all. Thank you, Madam.
Thank you. Thank you so much for giving me this opportunity. I hope students have got benefited at least by anyway. Your teachers must have explained you everything, but even if you get some more knowledge, that will be really encouraging.
Yes, ma'am. Thank you very much, ma'am. Thank you for
It's my
sharing your
pleasure.
knowledge to our students.
It's my pleasure.
So once
It's my
again, we
pleasure.
will organize one more webinar
Yeah.
like this way on this
Yeah.
particular topic. It will be a continuation of that, ma'am.
Yeah. Yes.
Thank you very much, ma'am.
Yeah,
Thank you
it's
very
my
much.
pleasure. Thank you, one and all, for giving me this opportunity.
Okay,
Thank
ma'am.
you.
You're welcome, ma'am. Students' feedback is posted in the chat box. You can fill the feedback and post it. You'll get all these certificates.